Okay, let's take a look at this problem here. We have a certain spring stores 10 joules of potential energy when it's stretched by 2 centimeters from its equilibrium position. So let's just start by extracting that information first. So we know that the elastic potential energy associated with the spring, this PE elastic, this is equal to 1/2 times K, the spring constant or the force constant, times X, which is really like a delta X. It's how much it's stretched or compressed from its equilibrium or unstretched position, squared. And it says that when X is 2 centimeters, when we have X equal to 2 centimeters, I'll put this in meters, so 0.02 meters, we have the potential energy, PE elastic, is equal to 10 joules, is what this says. So we could actually go ahead and find out what K is, I guess. We could find the spring constant, knowing that really this comes out to 10 is equal to 1/2 K times 0.02 squared. This means that K, solving this, K is equal to 50,000 newtons per meter. But of course, this wasn't actually what was being asked right away, so we kind of jumped forward a little bit here. But this was actually what they were asking in D. So they're asking, what is the force constant? So this is actually the answer to part D. I could have written this out here. This is K is equal to 50 kilonewtons per meter. I guess we could have written it out that way. But they actually ask us in part A, they ask us how much potential energy would the spring store if it were stretched an additional 2 centimeters. So I could, that would be 4 centimeters, right? So I could just, plug it in. I could plug it in over here, and we could find out, what the energy would be. But let's kind of do it with some proportional reasoning. So let's go back and do part A here. So let's say that we have the initial stretching. I'll call this like X naught. This was equal to 0.02 meters, right? And then for part A, the stretch for part A is going to be equal to twice this much, right? Or sorry, it was an additional 2 centimeters. So that's going to be 0.02 meters plus another 0.02 meters, and so that's equal to 0.04 meters, right? And so 4 centimeters. We could also say here that this is just going to be twice as far as the original one, right? So this is actually 2 times x naught. Okay, so if I go 2 more centimeters, then it's actually twice as far as that original stretch. And so then I can say that my potential energy in part A is going to be 1/2 times the spring constant times xa squared, right? But replacing xa with this 2x naught, this is 1/2 k times 2x naught squared. So squaring this 2 and this x naught, pulling this out, this becomes 4 times 1/2 k x naught squared, right? But this part here, this 1/2 k x naught squared, this was equal to the potential energy that started out, right? PE naught, which was 10 joules. And so we can see then that the potential energy for part A is equal to 4 times this 10 joules. And so that's equal to 40 joules. And this is the answer to part A. So you can actually just see here, if we look back at just the elastic potential energy, it's 1/2 k times x squared. What happened is that we doubled this part right here, right? So by doubling this, and then it gets squared, we quadruple the amount of energy stored, right? And so kind of just like we saw with kinetic energy, if I double this stretching, then it's going to be 4 times the energy. So it was 10 joules at first, 40 joules now for part A. Then part B, see here, part B, how much potential energy would it store if it were compressed by 2 centimeters instead? Okay, so now it's going to be compressed. So what we can do is we can say here, all right, so for C, we have XC is equal to a compression, so that's going to be negative. It's negative 2 centimeters, which is just negative how much it originally was stretched, right? So negative x naught. So then the potential energy at C is going to be equal to 1/2 k times xc squared, but that's equal to 1/2 k times negative x naught squared. And this negative x naught, when it gets squared, that's just the same thing as x naught squared, right? And so this whole thing over here, this 1/2 k times negative x naught squared, this is the same thing as just 1/2 k times x naught squared, which was just our starting potential energy. So we can see here that the potential energy at C is the same thing as that starting potential energy, which was just 10 joules. So this was the answer to part C, in which, you know, you can just kind of look at this too and say, well, it doesn't matter. You know, looking back at just our equation for elastic potential energy, it doesn't actually matter if it's stretched or compressed. If this is the same distance, then all I really care about is the magnitude of x, right? So compressed 2 centimeters, stretched 2 centimeters, same amount of energy is stored up regardless. And then in D, and by the way, we could have done all of these using the spring constant we found over here. We could have done all of these problems just by plugging that in, but we're doing this proportional reasoning instead. For part C, it asks us to find out how far from the equilibrium position would you have to stretch the string to store 20 joules of potential energy. So now, instead of saying how much energy we have, I tell you how much energy we want, and you tell me how far we need to stretch it. So in part D, I'm sorry, this was actually part B over here. This is part B. And now we're on to part C. Sorry about that. So this is part C. We already did D from the very beginning. So for part C, we want our potential energy to be equal to 20 joules. And so then this is 1/2 k times x c squared for part C, which means this actually should have been D, right? Okay, so 20 joules is 1/2 k times xc squared. I could say here, you know, we know what k is, so we can find out what xc should be, but let's do proportional reasoning instead. So this is going to be twice that original energy, right? And so I could say here, this is 2 times the starting potential energy naught. And that's equal to 1/2 k times xc squared. But I can write out the starting potential energy in terms of k and x squared. So this is 2 times 1/2 k x naught squared is equal to 1/2 k times xc squared, right? Now a bunch of things will cancel out over here. I have a 1/2 on both sides, I have a k on both sides. That shows up on both of these, so it doesn't, so it cancels out. And what we're left with is that we have 2 x naught squared is equal to xc squared. And so the amount of stretching I need for part C, when that's squared, it's going to be twice, x naught squared, right? So solving this, I can say here that xc is going to be equal to plus or minus the square root of 2 x naught squared, right? Which then I can take out that x naught squared and say xc is equal to plus or minus the square root of 2 times x naught. And so since the original stretching was 2 centimeters, this stretching for xc is plus or minus, because then we stretched or compressed, square root of 2 times 0.02 meters. And so this comes out to xc is 0.02828 meters, or this is equal to 2.828 centimeters, either way. So really what that comes down to is that I needed to stretch it square root of 2 times as far. Just kind of think about this, this proportional reasoning here. In order to have twice the energy, the stretch needed to be square root of 2 times as much. That way, once the whole thing gets squared over here, once this is squared, I'll end up with twice as much energy. And that's kind of the idea. So if I wanted to have 3 times as much energy, let's say I wanted to store 30 joules of energy, then I could just replace the square root of 2 with the square root of 3. That way, when it gets squared, I'll have 3 times the energy.